So in this video, we're going to talk about different substitutions we can make to help us solve a differential equation. And we're going to start by talking about homogeneous equations. When we talk about an equation that's homogeneous, we're talking about a function that if we were to substitute in for x and y, tx and ty, and we were able to pull out t to some power and then have the function f of xy, then we say this is a homogeneous function, and the degree would be that exponent on the t, whatever we were able to pull out. So this is different than there's two types of homogeneous differential equations. There's the homogeneous differential equations that we can think about this way. This is going to require a substitution. The other homogeneous is where we had that function, I'm going to call it f of xy, where that is the derivative is equal to 0. So we're not talking about that type. We're talking about the ones where if we substitute in tx and ty and we are able to pull out t to some power, we're going to have that original equation there, f of xy. So if we were to look at a first order differential equation that's written out in this form, so it's a little different than what we're used to seeing. We have some function in terms of xy, they're calling it m, times dx, plus another function in terms of x and y, times dy is equal to 0. This is said to be homogeneous if both those coefficient functions, that function m and that function n, are homogeneous functions of the same degree. So in other words, if we were to take m and substitute in tx and ty, and we were able to get m times t to some power out, and then do the same kind of thing with n by substituting tx and ty, and get n with t to some power out, and those powers are the same, then we say we have a first order differential equation that is homogeneous. And so if we do have a first order differential equation that's homogeneous, then we can use a substitution to help us solve this differential equation. So we can make the substitution y equals ux or x equals vy. Now, sometimes one substitution is better than the other substitution. You really don't know until you do trial and error. But in practice, you try to use x equals vy wherever the function m is simpler than n. Now, simpler kind of is a relative term. What seems simpler to you may be a little different than what seems simpler to me. But that's a good thing to try. If you think m is simpler, try using x equals vy. Otherwise, you can try to use y equals ux. Sometimes one substitution makes it easier to solve than the other substitution. Sometimes one substitution is impossible to solve, and would require the other substitution. And you just don't know those things until you do the substitution and you get into kind of the mix of what's going on there. So keep that in mind. And that's basically what I said right there. You may have to change your substitution. So let's look at a few problems here. So if we look at this problem, there's our function m, and there's our function n. So m of xy is equal to x minus y, and n of xy is just the function x. So to make sure this is homogeneous, we're going to substitute in tx and ty. So we're going to have tx minus ty. And notice we could factor a t out, and that's going to leave us with x minus y. And that is our m that we started with. If we look at n, and we substitute in, again, tx, ty, we're going to end up with tx. So that's the same thing as t times n of xy. So we've shown this is homogeneous, and the degree would be 1 because that is the exponent on the t. Notice in both cases we were able to pull out a t to the first power. You have to be able to pull out a t to the same power for both the m and the n. So this is homogeneous, degree 1. So to solve this, we're going to use a substitution. So to me, it looks like n is a little simpler, so I'm going to use y equals ux. So if we have a substitution for y, we also need a substitution for dy, and that dy substitution is going to come from taking the derivative of y. And that derivative is first times derivative of the second plus second times derivative of the first. So it becomes dy equals u dx plus x du. So now let's substitute all of this in. And remember, we're substituting it into our differential equation up here. So we have x minus y times dx plus x times dy is equal to 0. The goal with a homogeneous differential equation is to be able to separate the variables. And once we do that substitution, we should be able to separate. So I'm going to do some distributing. Notice the xu dx terms cancel. So we're left with x dx is equal to negative x squared du. So I'm going to divide both sides by the x squared. So I have dx over x on the left is equal to negative du on the right. So now that we've separated, we can integrate. So we're going to have the ln of the absolute value of x equal to negative u plus c. And we can solve this one for y. Before we do that, we need to make a substitution again. So notice we have everything in terms of x and u. Remember we said y was equal to ux. So what would u have to be? If we solve for u, we're going to get u equals y over x. So let's sub that in for our u. And now I'm going to multiply everything by x. And I'm going to get y by itself. So there's our final answer. Now we could have also done this using the other substitution, x equals vy. So just for fun, let's do that. So it's the same differential equation. And suppose we would have used x equals vy. So to take the derivative of x, so we have a substitution for dx, we're going to use product rule again. So it's the first times derivative of the second plus second times derivative of the first. So dx is v dy plus y dv. So now let's substitute that into our differential equation. So we're going to have vy minus y, and that's times dx plus x dy is equal to 0. So the goal is always going to be to try to separate the variables. So we're going to distribute. We have a binomial times a binomial here. So fronts, outsides, insides, last, plus x dy. Okay, hold on. We forgot to substitute in for this x here too. So let's go ahead and do that. So I'm backing up one step. That x is equal to vy. So then if I substitute in for this x also, I have vy dy. And this is a good place just to make sure that we did substitute everything in. Do we have everything in terms of v's and y's? And we do. So then we want to look and see if anything is going to cancel and reduce. The vy dy terms are going to cancel. So we have v squared y dy plus vy squared dv minus y squared dv is equal to 0. So I'm going to move all the dv terms to the other side. And then if I look at that right-hand side, everything has a y squared and a dv in common. So if I were to factor out y squared dv, I'm going to be left with 1 from the first term and a minus v from the second term. So now let's divide both sides by y squared. And then divide both sides by v squared. And now we've separated the variables. So I'm going to simplify just a little bit. We now have dy over y on the left. And if we look at that first, we look at this term. We have 1 minus v over v squared. We can separate that numerator. That is a legal thing to do. All we're doing is undoing the subtraction of 2 fractions there. That's why it's legal. And that would be the same thing as v to the negative 2 minus 1 over v. So if we integrate dy over y, we end up with the ln of the absolute value of y. When we integrate v to the negative 2, we're going to get v to the negative 1 over negative 1. And when we integrate negative 1 over v dv, we're going to integrate to get the negative ln of v plus c. Now, I like to clean up my negative exponents, so we're going to have negative 1 over v here. And then let's combine the ln terms. Our goal is going to be to solve this guy for y if we can. So I'm going to move this over to the other side. And we know we can combine those ln's. And this is a good place to go ahead and back substitute. We started out by saying let x equal vy. And we want everything in terms of x and y, not v and y. So we know v is the same thing as x over y. So this is going to give us the ln of the absolute value of x minus y over, is equal to negative y over x plus c. Multiply everything by x. Don't forget to multiply the c by x. And then solve for y. So you can see that's the same thing that we got when we did the substitution the other way. This process was just a little bit more tedious, still doable, but we could use for this one either substitution to get us to that final answer. And typically you'll be able to use either substitution to get you to the final answer. Let's do one more. Suppose we have x squared plus y squared dx plus x squared minus xy dy is equal to 0. And we're asked to solve. This one's also going to be homogeneous. We need to be able to prove that it's homogeneous. So this is our m. This is n. M is always attached to dx, n is always attached to dy. So make the substitution, tx, ty. So we're going to have tx quantity squared plus ty quantity squared. So it's going to be t squared x squared plus t squared y squared. And we could factor a t squared out, and that's going to leave us with x squared plus y squared. X squared plus y squared was our m. Looking at nxy, make the substitutions, tx, ty. So we're going to have tx quantity squared minus tx times ty. So that's going to be t squared x squared minus t squared times xy. And once again, we could factor a t squared out, and that's going to leave us with x squared minus xy. And that was our n to begin with. Notice in both cases, we were able to pull out a t squared. So we have shown this is homogeneous, and it's degree 2. So now we're going to do a substitution. To me, I don't really see a difference between the difficulty or what's simpler between m and n. So we could use any substitution. I'm just going to use y equals ux. We could use x equals vy, and we could see how it goes. I'm going to use this one. So dy is u dx plus x du. That comes from taking the derivative of this. And now we're going to make our substitution. So we have x squared plus y squared times dx plus x squared minus x times y times dy. And that's going to be equal to 0. So let's clean all this up. Remember, the goal is to separate the variables. If you have a homogeneous differential equation and you do your substitution, you should be able to separate. In fact, that's the whole point of doing the substitution. If one substitution gives you something that you can't separate, that means you need to try the other substitution. You will be able to separate one of the substitutions. We're going to FOIL here. So now we're going to look and see if anything's going to cancel. I see a u squared x squared dx that cancels. So I'm going to keep the dx terms on the left, and I'm going to move the du terms over. So if we look at the left-hand side, we could factor an x squared and a dx out. And that's going to leave us with 1 plus u. On the other side, we could factor out an x cubed and du. And that's going to leave us with u minus 1. So let's divide both sides by x cubed. And divide both sides by u plus 1. So now that left-hand side simplifies into dx over x. This guy is going to require some long division, so let's do that over here. Since the degree of the top and the bottom is the same, we can use long division to help us simplify so we can integrate. U goes into u one time, multiply back through. So we're going to end up with a negative 2 here. So this simplifies into 1 minus the remainder. It's a minus 2 because I have a minus 2 as the remainder over the divisor, which was u plus 1. And now we can integrate each piece. So this 2 is really the exponent on that argument u plus 1. And since that's a squared, we're always going to have a positive, so we can drop the absolute value there. So I'm going to go ahead and do my substitution here. So we're going to do that back substitution. Remember, we said y equals ux. So u is equal to y over x. So let's see if we can clean this up. This is a pretty messy solution here. My goal is to try to get rid of those LNs if I can. I don't think we're going to be able to solve this for y because we have a y inside the argument and a y outside of the argument, so it doesn't appear like we'll be able to do that. But we can probably get rid of those LNs. So if I combine those fractions, you got to have a common denominator. That's going to be x, so we're going to have y plus x over x. So now let's move this ln to the other side and combine those. So we can combine these ln's using that multiplication property. So it's going to be x times y plus x over x quantity squared. Just simplifying that. This is y plus x squared over x squared, and you can see how these x's are going to simplify. So now we can rewrite this as an exponential. So we have e to the y over x plus c. All that's in the exponent is equal to y plus x squared over x. I can rewrite this as e to the y over x times e to the c. E to the c, if I take a constant and raise it to a constant, I just have another constant. Since it's different than what this c would be, I'm going to call it c1. And then let's multiply both sides by x. So this answer is a little bit nicer to look at than the one with ln's. So a lot of people usually ask in differential equations, where do I stop simplifying? So if you can solve for y, you should always solve for y. In this case, it's not possible to solve for y because we have a y in the exponent of the exponential function and a y that's being squared inside of this term. So it's a little different than the last one. The last one we could solve for y. So then you ask yourself, can I get rid of ln's? If you can get rid of ln's, then you definitely want to do that. And in this case, we could get rid of ln's. And then there's just not a lot more we could do with that. So we're just going to leave it that way. But to kind of give you guidance to answer that question, solve for y if you can. If you cannot solve for y, then try to get rid of any ln's or simplify any fractions if you can.